Hi everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 12 of my course, the SQL Server on VMware Accelerator. We just wrapped up a massive deep dive on performance tuning SQL Server in your virtual environments. Let's talk about the fun topic of SQL Server availability in virtual environments. In this module, we're going to talk about some of the really not so glamorous but absolutely vital architectural design decisions that you need to make around running SQL Server in VMs. You should have done a lot of these already, but these decisions can potentially change when running in a virtual platform. We're going to start by helping you define your recovery point and recovery time objectives. We're then going to review the high availability options that the VMware platform provides to see if this is good enough. If it's not good enough, we'll then talk about the SQL Server high availability solutions that we can use to complement what VMware already provides. We'll then talk about the specific tuning for certain SQL Server high availability solutions, such as failover cluster instances and availability groups. We'll also talk about how VMware level disaster recovery features might, in some situations, alter or change your disaster recovery architecture for your SQL servers. We'll also talk about some tricks that I have around restoration testing, as a backup or a disaster recovery strategy that has never been tested is not really a backup. Your professional duties as a database professional start here. Databases must be up and available to the end users and your applications in their entirety with no interruption of service or corrupt data, period. As soon as it's up, then it has to be fast enough to fulfill the demands of the end users at a fast enough rate to be deemed acceptable. These two facets are your two primary duties when managing these servers. The business continuity strategy plays a large part in defining the availability of the platform. Part of managing these platforms is to understand your strategy and response for handling these issues, no matter the scope and the scale of the incident. This can be for both planned and unplanned incidents. We can start with micro-level continuity features around backup and restores. This is usually related to database-level problems. We then move to a high availability solution if a single component of a larger scale starts acting up. Finally, if we have something large enough to declare an actual disaster for, how does our SQL Server continuity strategy fit within the larger organizational strategy? Before you start selecting any SQL Server or platform availability features, throw away the tech and ask your C-level to define a couple of key metrics that you will engineer the continuity strategy to meet or exceed. The first is the recovery point objective, or RPO. This metric is usually measured in minutes or hours and defines the amount of data the organization is willing to lose, at most, if a critical system were to fail. The next is the recovery time objective, or RTO. The metric is also usually measured in minutes or hours and defines how long a critical system can be down, at most, before the business starts having a really big problem. I cannot stress hard enough that these organizational SLAs must be defined by your C-level management. I even joke, but I'm not really joking, that your upper management needs to have defined these values, printed a document stating these SLAs, and all signed it. This is the document that you will use to engineer your business continuity strategy. If your organization has not defined either of these SLAs, I'm not exaggerating when I say they probably don't have a good understanding of availability in general. What I mean by this is without these defined, the unwritten expectation is that in the event of a massive disaster, either small or large, is that you will lose no data and that the systems will be up and running immediately. I know you've been in this for a while and you know how unreasonable these expectations are, but people change when their business is down for any reason. If you have the defined service level agreements that they have agreed to and physically signed, you're able to point to that piece of paper and say, we have built your business continuity strategy to meet or exceed these values. And if you've done any amount of routine testing, you're able to show the recovery time of any of these components. You'll be able to tell them that the business will be back up in a certain time frame and that they need to go get some coffee and chill for a little bit because you know when it's going to be back up. Once you have the service level agreements defined, then we need to figure out, based on our current platform, what are the availability options that will keep us in a supported state. Not all SQL Server availability features will run with all of the VMware level features enabled for all versions of VMware. The last thing we want is to call either of the companies with a support request and have them fail to honor their support. For the record, VMware does not certify specific versions of SQL Server. They'll certify a version of Windows or Linux and assume that since SQL Server is supported on certain modern versions of those operating systems, allow that level of support to pass through it. So if you're looking for an official support statement for this specific version of SQL Server that you're looking to run, you're not going to find one. VMware does have a compatibility guide that you can find at the link on the screen with a full compatibility matrix of all of the hardware and configurations that they do officially certify. Microsoft also has a support policy for virtualization at the KB article on the screen, as well as a support statement for non-Microsoft sourced hypervisors. Don't let either of these scare you. It's there to say that if there are issues at the virtual layer, that they reserve the right to have you resolve those before they resolve the potential issues with something within their own scope. Feel free to read up on both of these knowledge base articles for your understanding. I also want to make sure that you understand what their service level agreements might actually mean to you. Many times these SLAs are dictated in terms of number of nines per month or year. I personally don't like this particular metric as it doesn't quite convey the severity of the issue based on a certain percentage. When they say a metric such as 2 nines, they really mean 99% uptime. If you look at the chart on the screen, you'll see that a 99% uptime guarantees can equate to up to 3.65 days or 7.31 hours of downtime per month. 99% sounds pretty good, but 3.6 days a year sounds really bad. If that 3.6 days occurs in a row, you're about to have a really bad day because now your business is down for almost 4 days straight. As we start to increase the number of nines, such as 3 nines means 99.9%, you can see how the actual downtime hours and minutes decreases dramatically over that time span. The higher the number of nines usually means we have to start leveraging multiple availability and disaster recovery features at multiple layers, all of which means you're probably spending a lot more on your business continuity strategy. Now let's take those guarantees and break this down into 2 components. They might have already done this as part of their availability goals. The first is going to be a high availability mark. Usually when I discuss high availability, I usually mean a localized issue where a single component fails or has a problem. The scope and the scale of the issue can be limited to certain smaller impact devices. It still means we have a problem where databases may not be available, but it could be something like a Windows or a Linux operating system has an issue after a misconfiguration, or we have database corruption for whatever reason. Disaster recovery generally means a much larger in-scope event with much more severe organizational impact potential. It could be something like a data center fire or natural disaster like a tornado. I personally live in Tornado Alley in the middle of the US, and we have had a number of close calls with tornadoes. Even a natural disaster nearby can knock out power or rupture natural gas lines and cause an evacuation. We also need the organization to help us understand certain scenarios around both planned and unplanned events and the expectations around them. Sometimes we may even want to factor in the conditions around an outage into our service level agreements. Many organizations that we work with will take their service level guarantees for their customers and split out the time for planned outages as part of routine maintenance. Everyone needs to have a routine planned outage window for things like SQL Server and operating system level patching, SQL Server and application upgrades, firmware updates, hardware driver updates, operational or design changes, or pretty much anything else you can think of that you need to do but never get the opportunity to do. Many organizations that we work with do not have clearly defined outage windows on a monthly or quarterly basis, so many of them just don't patch anything. In today's security-conscious climate, that is simply not an option. Then the unplanned outages can occur, such as operating system failure or SQL Server instance level issues, host failures that may knock out a virtual machine for a short period of time, or any other small or large-scale issue that we can't prevent or predict. None of these issues are any good, but the scope can be small or large. What I would love for people to do is to work through certain scenarios that you would consider the most common. If you can determine the most common scenarios for some of these issues, you can work up specific plans that might change based on your scenario. For example, it's fairly inevitable that someone somewhere will issue a delete statement and forget the where condition. Somebody might drop a table in the wrong database. We may have a hiccup in the platform and get database corruption. We might even have an insecure website that gets nailed by SQL injection. All of these means we have to have the quick mechanism to restore a database. Other times it could be that we need a highly available platform for situations where the operating system may be unresponsive, or maybe we need availability through replicas for SQL Server or operating system patching to minimize our outage window. It could also be for hardware maintenance. Other times we could have things such as a SAN failure, power outages if we live in places that are prone to that, data center fires, or other natural disasters. I've got one company that we're working with right now at the time of this recording that has an older building with their data center in the basement. The water main pipe into the building is running in pipes directly on top of their server racks. If this pipe were to rupture, their entire IT infrastructure would be destroyed in less than a second. Other companies that we work with have their data centers located near major fault lines on the west coast of the US. All of them have specific response plans for earthquakes in their business continuity strategy. If you can clearly define some improbable yet possible scenarios that you would rank higher than others, you can start to define an action plan. With that plan, we can now start to leverage availability and disaster recovery features in all of the layers of our environment to put together the right response for the most common scenarios. If you've ever worked with SQL Server availability options, we have tons of features built in the platform that do a very good job. SQL Server's high availability options include failover cluster instances, or FCIs, availability groups on top of FCIs, and the deprecated feature of database mirroring. Some people look at database mirroring unfavorably, but I'm pretty neutral on it. It does work quite well for what it's intended to do. Other people might look at log shipping as a high availability solution. If this meets or exceeds the SLAs set for a given database, sure, why not? Many of these can also be used for disaster recovery purposes. Asynchronous availability groups or stretched failover clusters are pretty solid business continuity options. We can also use database mirroring in an asynchronous architecture. We can also do log shipping. You'll note that for both of these, I say that replication is not a business continuity feature. That's because it isn't. Many SQL Server performance engineers state that the destination may not include every single transaction that occurs on the primary site. The word on the street is that roughly 1 in a million database changes may not make it to the destination. If you're using replication to see data that is used for business-sensitive decisions like financial reporting, you may want to look to either verify and validate your data periodically or perform refreshes on a somewhat frequent basis. The VMware layer has a number of business continuity features as well. You should understand the high level of what each of these do so that you know when and where to use these features in case they may complement or in some cases replace the SQL Server level business continuity feature. VMware High Availability is a feature that we've already talked about as part of the cluster setup. If a host fails, the virtual machines that were running on that host do go down, but they are immediately restarted on the remaining good hosts. Another one that I haven't talked about so far is VMware Fault Tolerance. Let's talk about this feature now. VMware Fault Tolerance is a fascinating technology that allows two virtual machines to be running for a truly fault-tolerant architecture. The primary virtual machine is up and running just like it normally would be. The second virtual machine is running on a different host and is linked to the primary server's virtual disks. All activity for CPU and memory are synchronously mirrored to this other virtual machine. If for whatever reason the host were to fail underneath the primary virtual machine, the secondary virtual machine is immediately failed over to. In theory, this provides a highly available platform that results in no interruption in service if that host were to fail. The challenge with this architecture is that there are a significant amount of drawbacks. First and foremost is the performance overhead. VMware will not publish an expected performance overhead guideline. My experience has found it to be a roughly 1/3 of the performance is removed. For just about every production SQL Server that I can think of, this amount of overhead is just not acceptable. I'm not blaming VMware at all for this, as this is an incredibly tough engineering feat with what they've already accomplished. For some workloads, such as routers and load balancing appliances, this particular concern wouldn't be that big of a deal. For our SQL servers, it's a deal breaker for most of the machines that we manage. It is also not a replacement for SQL Server high availability features. It will not provide you high availability when you need to do things like patch the operating system or the SQL Server instance. Whatever happens in the primary virtual machine gets transmitted to the second machine, including commands for reboots. In theory, you would still need to complement this level of fault tolerance with the SQL Server high availability feature if you want to minimize the impact of those operations. However, the use of a failover cluster instance or an availability group are explicitly not supported. It also has a limit of just 8 virtual CPUs. Some SQL servers would run just fine with this limit, but others would never be able to squeeze into that much of a smaller footprint. So, in practice, VMware fault tolerance just doesn't work for SQL servers. Leveraging VMware high availability underneath the SQL Server high availability solution does help us because it minimizes the risk window if a hardware component were to have a problem. VMware and the underlying platform components also have some high availability features that work quite well. If your SAN supports it and you have an equivalent SAN at your disaster recovery facility, you can do SAN LUN-level replication from one SAN at the primary facility to another SAN at a disaster recovery location. This will replicate all of the contents of the LUNs to the disaster recovery facility. You can also choose to replicate the virtual machines themselves either through vSphere replication or other third-party utilities. We do this at the virtual machine level so that all changes are tracked simultaneously so that your databases are transactionally consistent. You can also perform the same level of replication from inside the virtual machine. Many of the cloud providers have agents that can be installed inside the operating system that will replicate changes to a cloud provider inside virtual machines there and have them ready to recover at a moment's notice. The biggest thing that I want you to realize by listing out all of these features is that this is not a one-stop shop for SQL Server business continuity. You have a lot of different options and features available to you. You should start understanding our SLAs and pick the appropriate solution for the major scenarios. Let's start talking about the lowest level, backups and restores. And no, backing up to a USB drive and carting it off-site periodically is not a backup. The goal of a database level backup is to provide point-in-time recoverability of your data. It's performed per database. SQL Server has three primary means of performing these backups. If you spend any amount of time managing a SQL Server, you should already be quite familiar with each of these. The first is the full database backup. It provides a complete point-in-time backup of the database and the contents of the transaction log. The next is a differential backup that contains a backup of the changed data since the last full backup. In order to restore this differential backup, you still need the last full backup first. The next is a transaction log backup. It provides a point-in-time backup of changed data since either the last full backup or transaction log backup. These should not be strange terms for you. What we do really need to focus in on here is how these interoperate with your virtual machine layers. I've mentioned this before in this course, but you really need to work with your platform administrators to make sure that your backups are on a different failure domain than your primary SQL servers. Are you writing your SQL Server database backups to a different machine on the same underlying storage? How frequently are these being retrieved and moved onto a backup archival mechanism or even copied off-site? If they're being written to on the same storage and that storage layer is being copied off-site once a day, then your recovery point might be as late as 24 hours instead of the 5 or 10 minute transaction log backup frequency that you're used to. Whatever you do here, understand the single points of failure in your environment and make sure that you have the least centralized failure domains possible for your database level backups. Review your SLAs and review your budget and distribute your backups appropriately to exceed your SLAs. Many organizations that I see will back up to a share on a virtual machine that acts like a file server. What they generally don't think of is that this virtual machine is on the same SAN. Thankfully, they're getting it off the primary SQL Server in case that VM were to have a problem, but if the underlying storage were to have a fault, they'd be in a whole world of hurt. A simple solution if they don't want to write the database across the network to a different device is to back up their databases onto a virtual disk connected to the same virtual machine, but that virtual disk is actually placed on a different underlying storage device. It could be a lower powered SAN or a high capacity NAS. This would reduce the risk associated with a single storage device failing. Or, for even more separation of duties, they could write it to a network share on a different virtual machine or device that's on a different storage subsystem. As long as your risk is minimized, these are all viable options. It just depends on your level of risk and your budget. To me, my backups have three distinct layers. All three of these need to be tested and validated routinely. You, the data professional, have been managing your database backups for quite some time. You know that with the backup options that are listed, you get point-in-time recovery with any of your database data. We should also be concerned about an operating system level backup. Unless you have every single nuance of the underlying operating system and the SQL Server instance documented and readily scriptable in case you need to redeploy the machine, if you don't have an operating system with SQL Server running in it where you can restore your databases into, in the event of an emergency, you're redeploying the underlying operating system and reinstalling SQL Server. My experience shows that the time taken to perform this step usually exceeds a high availability requirement from the organization. The last layer is with the virtual machine backups. If I don't have a good virtual machine layer backup, then I'll have to spin up a new virtual machine in the exact configuration that I expect in order to be able to perform an operating system level restore before I can recover my databases. My database backup methods should be pretty clear for you at this point. SQL Server has native backup functionality built into it where you can perform database backup and restore features with no additional software needed to configure during an emergency. These are just simple backup and restore statements. This does not provide you central management for all of your SQL servers. You might be leveraging third-party software to assist you with your SQL Server backups and potentially provide centralized management features. There are a lot of pros and cons about this type of software, which I won't get into here. My only hesitancy with this is that you must install this software prior to being able to restore any databases during an emergency. Most of the time, it's not that big of a deal, but you need to have the software and its installation key readily available during an emergency. I've seen horror stories where the subsystem went down that contained this software and its license keys, and it was hours before the database backup software could be reobtained and reinstalled before the databases could begin to recover any of the databases. The last level is with your virtual machine level backups. Some virtual machine level backup software claim to be able to perform a SQL Server level backup appropriately. There are only a couple out there that I would actually trust, as they were built with DBA requirements in mind. Most of the time, the software is built so that it grabs the virtual machine disks at the same time, but has no ability to manage the SQL Server transaction log properly. Let's take a look at this process. The process to back up a virtual machine is pretty straightforward. In normal operational times, each virtual disk cannot be read by external processes. The hypervisor then takes a snapshot on each virtual disk on the virtual machine so that external processes can start to read those files. Just in case anything inside those virtual machine changes, a virtual machine delta disk is created for each virtual disk. This is what allows my backup program to be able to read the underlying virtual disks without interruption. The snapshot layer is the mechanism that allows the hypervisor to place all writes into separate delta disks while still being able to read from the underlying disks to keep the space consumed down. The process then reads the individual virtual disk. It's able to get a good copy of the virtual machine while any changes to the virtual machine disks from within inside the operating system get fed into the snapshot delta disk. As soon as the backup process is completed, all of the blocks inside the delta disks are then written inside the virtual machine disks. The delta disks are then removed and the process goes in reverse. The VM is now back to normal. This is the normal process your virtual machines go through every single time a virtual machine level backup is taken. VMware does have an interesting feature that makes this process faster. VMware introduced a feature called Changed Block Tracking, or CBT. CBT allows the hypervisor to track the individual blocks that have changed inside a virtual machine disk. Once a SQL Server machine backup agent has taken a full backup copy of the virtual machine disk, all it has to do is to read the blocks contained in this list of changed blocks. It makes a backup much faster, and once it's done reading for that backup, it just resets that list of what has changed. The tricky part is that snapshots in general can cause a bit of a concern. During the parts of a snapshot where the snapshot is either taken or removed from a virtual machine, it can cause the virtual machine to slow down briefly during what is called a stun operation. The stun operation is designed to decrease the amount of activity in the virtual machine so that the hypervisor can keep up with that change and write those contents to disk. If your hypervisor is severely overloaded and your CPU scheduling times are high, this operation can take longer than expected. If that happens, it may slow the VM down enough to where the SQL Server high availability solution could have an issue and potentially fail over. Most of the time, this is not that big of a deal, but if you find that your virtual machine backup is interfering with your SQL Server high availability solution, go talk with your virtual machine admins to see if there is something they can do to minimize the impact of the VM level snapshot. Other virtual machine backup features can attempt to make that backup set what is called crash consistent. Crash consistent basically means that they're taking the pointer of the virtual machine disks at a certain point in time. While this sounds good, it's not good enough for SQL Server. We don't just want crash consistent. We want application consistent, because simply being crash consistent does not provide any application awareness for the apps inside the operating system. Making these processes what is called application consistent involves the use of volume shadow copy services, or VSS, inside the operating system to flush any pending storage operation to disk at that point in time. Inside your SQL Server error log, you might see occasional entries for something that looks like a command that is, quote, freezing and thawing a storage operation. If you look at the start and stop times on it, it should not be more than about a second. This is the VSS operation at work. It's a command that the backup system can tell the operating system to perform to flush all pending storage operations to disk and to hold making any new ones until that pointer is taken. These actions are what we want to see during virtual machine level backups that come up, but we don't want to see them cause a delay long enough to cause a SQL Server transaction to time out and cause issues. Occasionally, I hear of storage admins talking about how they're taking SAN LUN level snapshots as a backup. I'll say it a million times. A storage level snapshot is not a backup. It's a fancy mechanism that can allow a very quick recovery to a previous point in time on a SAN LUN. All of the blocks that have changed after a SAN LUN snapshot has been taken or tracked and can be reverted. It's a fantastic mechanism to allow you to quickly roll back in the event that something goes wrong. From a SQL Server perspective, however, this provides us multiple problems. One, this is not a backup in that if the storage device crashes, all of these so-called backups are lost. If just the snapshot fails, it also means that any SQL Server transactions that have occurred since the last snapshot was taken are gone as well. Second, this provides us no SQL Server transaction log management functionality at all. A SAN LUN snapshot is a great way to provide a quick rollback mechanism and should be used when appropriate. It is not an actual backup. Don't ever let a storage administrator tell you otherwise. The next layer to worry about is when your different backups occur. The runtime schedule and durations need to be monitored so that these operations do not incur at the same time. Database backups are usually performed either nightly or weekly, and if weekly, differentials are usually performed nightly. Transaction log management occurs around the clock. Virtual machine level backups usually occur nightly or weekly as well, especially if your environment is sensitive enough where the snapshot operation can cause the application to disconnect or SQL Server availability features to fail over. Work with all the teams involved with all of these components so that the virtual machine level and the database level backup windows do not overlap or compete. It's usually pretty easy to keep these apart. Now, a backup is not a true backup unless it has been restored and validated, preferably in an automated fashion. Performing restores of database backups are pretty straightforward and should be second nature at this point. You should also be involved in the virtual machine level restores. Normally, if you're recovering a virtual machine for a production server, it's a two-part restore. You recover the virtual machine, and then you restore the databases to the desired point in time. You need to be involved in the process of recovering the virtual machine so that you know what recovery point to restore from. You might have a backup vendor that claims to be able to perform both layers in the same backup interface. I wouldn't trust it unless you can see it and test it and have access to perform this on your own. There are several on the market that I actually do trust to be able to perform these operations together, but I'm not going to market for them here. Simply test any of their claims to validate that they perform as you expect. If there are any challenges in the process, perform your backups as a two-part backup. Back up your virtual machine and back up your databases separately. Your restores then become that two-part restore. Now let's start talking about SQL Server and VM level availability features. I listed them off before, but I'll display them again. SQL Server has a failover cluster instance and availability groups. Some people still might use database mirroring or log shipping. VMware provides VMware high availability and fault tolerance. Again, fault tolerance probably isn't a good fit for these servers, but the high availability feature might actually be good enough. Like I mentioned before, VMware high availability is where if a host were to fail, the virtual machines that are on that host are down, but they're restarted by vCenter onto the remaining host in the cluster. In some environments, this level of responsiveness might actually be good enough. I claim that the approximate outage window before SQL Server is back up and listening for connections is approximately 2 minutes and 45 seconds. Is that good enough? Think about your scenarios. Is this good enough for handling unplanned outages? It may not be sufficient for operating system level reboots, though. The reason that I feel strongly that this feature should always be enabled is that it reduces your risk window underneath the SQL Server high availability solution. Think about it. If you have a 2-node failover cluster on physical equipment and one main board were to fail, you now have a 1-node failover cluster until the vendor can repair the failed piece of equipment. That level of risk may not be tolerable to a business where this system is highly critical. VMware High Availability allows that secondary node to be restarted on a known good server within just a few minutes. The level of risk is reduced because the risk window is dramatically shortened. Make sure to work with the virtual machine administrators in that they use anti-affinity rules to separate the highly available virtual machines onto different hosts. I've already talked about how simple that is. Just make sure you review all failure domains that we talked about earlier. Now let's talk about some specific tricks for improving the availability of Windows Server failover clusters, which are usually present underneath both failover cluster instances and availability groups. A Windows Server failover cluster, or WSFC, is most likely present underneath a failover cluster or an availability group. All of the servers participating in the failover cluster should be as identical as possible. This includes in-guest operations such as operating system level patches, software, or other management agents. It also includes virtual machine level configuration details such as storage controller and virtual disk connections, network adapter types, and virtual machine CPU presentation. Whatever you do, your cluster must pass the failover cluster validation process in order to be a supported configuration. If you're going through the setup process, after it validates, it presents a report showing that this server has passed validation. Save a copy of that report into a location that is easily accessible if you ever have to contact Microsoft or VMware for support on this server. If you didn't generate one on existing servers, go back and revalidate and save off a copy of that report. The failover cluster uses a very rapid stream of heartbeat communication pings to allow the nodes of a cluster to communicate to make sure that they're all available and ready to work. This heartbeat stream is incredibly sensitive to interruptions in communications. Unfortunately for us, that also means that routine virtual machine layer operations, such as a snapshot being taken on the virtual machine, might interrupt this heartbeat stream just long enough to trigger a fault. The default settings are for both same subnet and cross-subnet options. The default values are called fast failover and are designed to respond virtually immediately if there are issues. If you run the PowerShell command on the screen, you can see the settings that your particular server is using. These were Windows Server 2019 servers where the same subnet threshold is 10 pings and the same subnet delay is 1,000 milliseconds. The cross-subnet delay default is 1,000 milliseconds and the cross-subnet threshold is 20 pings. I claim that these settings are a little too low to withstand routine virtual machine level operations. These are also settings that you should tweak a little if these servers are based in the cloud, as it's nothing more than virtualization in somebody else's data center. We need to bump up the settings a little bit. My starting point for tuning is to set the same subnet delay for 2,000 milliseconds and the same subnet threshold to 20 pings. Do the same for the cross-subnet delay. There's an additional setting that is not displayed called the route history length that, per Microsoft's recommendations, should be set to twice the setting for the same subnet threshold. Test and run the commands on the screen to set these levels appropriately for your environment. You can rerun the get cluster subnet command to see the resulting settings. You only need to run this once on any member of the failover cluster as it's inherited at the cluster layer. Now let's talk some specifics about a failover cluster instance. First of all, let's talk through a failover cluster instance architecture. To simplify things at first, let's present this as if these were physical servers. On a shared SAN, LUNs are provisioned to act as my shared disks for my SQL Server data and log objects. A couple of servers are provisioned and these disks are connected to the first server. When I spin up my second server, I connect my SQL Server object disks to the same LUNs connected to my first server. This becomes my shared storage mechanism for my SQL Server failover cluster instance. You then create a Windows Server failover cluster between these two machines. You configure a virtual IP address that points to the primary node in the Windows Server failover cluster. This failover cluster understands how to disconnect and reconnect the shared storage so that one of the two servers owns and it can access the storage. The second server knows that the storage is present, but it can't access it. A quorum disk is configured between the two node members so that it can act as a tiebreaker to allow one member to be promoted to a secondary if the second were to fail. At this point, the SQL Server instance is installed. The first server is configured as a failover cluster instance, and the second server is installed like this a little bit differently so that it becomes a second member of the failover cluster instance. A virtual IP address for this service is provisioned and managed by the failover cluster itself. This virtual IP address is then available for the applications to connect to. If we need to perform a failover from server A to server B of this SQL Server failover cluster instance, the services get shut down gracefully on the first server, the storage swung over to the second server, and then the SQL Server service is started properly on the second server. This process can take anywhere from 45 seconds to 3 or 4 minutes, depending on your server architecture and the speed of the underlying storage. These are not trivial architectures and can potentially cause greater level of outages than a standalone instance at the end of a given work year. Now, repeat this architecture using virtual machines with shared storage presented within your virtual layer, either through RDMs, vVols, or shared VMDKs if you're on vSphere 7.0 with fiber-connected storage. The rest of the architecture really doesn't change. VMware has some very specific guidance for virtual machine construction for failover cluster instances. You can reference a link on the screen for more details that will take you straight to a setup document from VMware Corp. Please note that this document is a little squirrely and that all the references to MSCS should be replaced in your mind with references to Windows Server failover clusters. Microsoft Clustering Services has not been an actual term in service for years, but VMware hasn't quite gotten the message and fixed this document yet. PV-SCSI controllers are fully supported on all shared disk controllers, including those for our RDMs, and should use this controller to maintain performance. All virtual machine network adapters must use the VMXNet 3 adapters and enable Windows receive-side scaling inside the virtual machines. There's also a setting related to storage timeout within the registry that needs to be updated to at least 60 seconds or more. The virtual machine level time synchronization settings should be forcefully removed so that only Active Directory manages the time synchronization for these virtual machines. See Module 7 for the specific details on how to remove this unfortunate quirk. A common NTP server should also be used inside the virtual machines. Usually this is not that big of a deal as Active Directory will just handle it, but confirm that they're using the same NTP server. You must also work with your virtual machine administrators to set cluster-level anti-affinity rules to separate your virtual machines onto different hosts so you maintain your high availability strategy. I know I've said that a number of times now, but it really does matter. If for whatever reason you're using in-guest presented storage for your failover cluster, which is supported but I'm not a particularly big fan of, there are a few things that you really need to accommodate in your design. Failover cluster instances can leverage SMB3 shares for the shared cluster objects, as well as in-guest presented SCSI storage. For any of these scenarios, make sure to leverage jumbo frames inside the virtual machine network. Every single hop between the virtual machines must be configured for jumbo frames and validated, but this is the only way you're going to get the maximum possible throughput potential from your virtual machine network to the storage and back. Dedicated virtual and physical network adapters are highly recommended to isolate the storage traffic and provide the highest possible levels of performance and availability. Virtual machine network multipathing is also recommended within the guest virtual network adapter teaming to improve redundancy and resiliency for these network adapters. These are just as if they were physical network adapters, and the appropriate architecture must be applied. If your failover cluster is using storage spaces direct or S2D, these are similar concepts to a hyper-converged network-based storage appliance. These are treated as independent virtual machines with very high networking speed requirements. I'm personally not a big fan of storage spaces direct because it overcomplicates an already complex environment. In addition to monitoring all of your network traffic and storage performance, you have to monitor your CPU activity inside the virtual machine. Jumbo frames can help reduce the CPU associated with high-speed networking activity. The same goes with receive-side scaling. Microsoft highly encourages the use of physical network adapters with a feature called Remote Direct Memory Access, or RDMA, enabled, plus a pair of virtual RDMA network adapter. Support for these on the VMware platform has just recently taken hold, and you may not have this present in your environment yet. Microsoft requires at least a 10 gig network adapter present for storage spaces direct and recommends at least a 25 gig or faster network connection. This can be hard to come by for your virtual environment, at least at the time of this recording. Now let's start talking about SQL Server availability groups. I'm going to introduce you to availability groups by starting with the architecture behind database mirroring. While database mirroring was deprecated in SQL Server 2012, it's still present in the SQL Server availability options as of SQL Server 2019. Let's review its architecture to learn why certain facets of availability groups are designed the way they are. Okay, 2 virtual machines are provisioned. Independent virtual disks are connected to both of these virtual machines. A normal SQL Server instance is installed on both of these. Now we're going to start setting up database mirroring. Database mirroring allows for each independent database to be replicated to another server, either synchronously or asynchronously. Each database's replication stream is independent from the others. A witness server is present to watch both SQL Server instances in case one were to fail, so it can trigger a failover on the remaining member. The hardest part with database mirroring is not with the mirror itself, it's with the application server. The application server has to understand how to connect to both SQL Server instances. It'll try to connect to the primary, and if it can't, it has to know how to fail over and connect to the secondary. I think Microsoft assumed that this would be a pretty straightforward thing for applications to modify when this feature was introduced. Unfortunately, however, application vendors either resisted or were lazy, and very few of them actually implemented this properly. This means that the challenging part of this architecture is making sure that the application is pointed to the correct replica. The other hard part is that if something interrupts one database's replication stream and the database fails over, not all of them come over with it. What if you're running a database-driven application such as Microsoft SharePoint that has multiple databases that all have to be online in order for the solution to work properly? If one database fails over and the others don't, the application's going down. The virtual machine architecture is extremely similar. Just replace SandLines with virtual disk. Nothing else changes. Availability groups take some of the high points from both failover cluster instances and database mirroring and combines them to provide a more resilient, flexible platform. First of all, make sure you call this an availability group or AG. It is not AAG or AOAG. Some members of the SQL Server community online will rip you apart for using this terminology incorrectly. I don't want you to have to deal with their wrath, so make sure you get the terminology correct. Also, if you're talking to other data professionals and misuse one of these terms, they might think less of you by doing so. To set up an availability group, spin up a couple of new virtual machines. These are independent of each other at this point. They get their own virtual disks. These disks can be on the same underlying storage or different underlying storage device. If your budget allows for it, put them on different underlying SANs to minimize the risk of storage failure. Install SQL Server in each of them just like you normally would. Now create a Windows Server failover cluster. Do not connect any shared storage. The failover cluster can be optional, but most folks deploy them with the failover cluster. The failover cluster's role is to facilitate failover and update certain pointers and objects inside Active Directory and DNS. Connect the failover cluster to a share on the network on a different device that is acting as a quorum and is called a file share witness. It becomes a tiebreaker in the event of a quorum tie during a failover. Now configure the SQL Server instance to what's called Always On Aware. The SQL Server service is restarted after this checkbox is enabled, and now we can provision what's called an availability group. An availability group is a group of one or more databases that are governed by the same set of availability rules within the SQL Server engine. These can be replicated either synchronously or asynchronously to one of the secondary replicas. At the time of this recording with SQL Server 2019, we can actually have up to 8 secondary replicas in a mixture of synchronous and asynchronous replication. If you would like to configure one, a listener can be configured on the availability group. It acts as an entry inside DNS and Active Directory that becomes the virtual object that you connect your applications to. As the availability group fails over to other replicas, this listener is updated to point to the primary replica so that your application level connection strings never need to be modified. One of the best things about this architecture is that you can have multiple availability groups present between your servers to allow you load balancing or more flexibility, whichever you need and whatever your licensing allows. Your virtual machine administrators need to be aware of the logical architecture of an availability group and to demonstrate the platform requirements needed. The networking is very sensitive between these servers, so if there are any network interruptions between them, you could have an availability group failure and your databases go offline. With this level of education for your virtual machine administrators, it should help them understand what comprises an availability group and allow them to make changes to the ways they operationally manage these servers. It can be simple tasks such as installing Windows-level patches in a serial instead of parallel manner. It could also be more complicated tasks such as virtual machine-level backup staggering, risk management with failure domains across things like blade servers or storage devices, or anything else they manage. One little tip that I find that helps here is that if you select the file share witness, right-click and hit Properties, go to Advanced Policies, and we want to run this resource in a separate resource monitor. The sensitivity to this device is equal to what the failover cluster itself encounters with routine, normal virtual machine level activities. I find that when you perform tasks like virtual machine level reboots for patches, running this in a separate resource monitor makes the cluster less sensitive to when this file share witness resource goes offline briefly. Whew, now let's talk about some disaster recovery options. I find that virtual machine level disaster recovery is a lot more friendly than virtual machine level high availability as a replacement. The different layers of features are almost always complementary, but VMware level disaster recovery features might actually replace your SQL Server DR architecture. I say this carefully because I don't know your recovery SLAs, but in a lot of environments that we work around, virtual machine level disaster recovery features fall well within the defined SLAs for disaster recoveries. SQL Server gives you some great disaster recovery options, such as backing up your databases and copying them over to a different facility so you can restore them, an extended failover cluster instance, an availability group configured in an asynchronous architecture, database mirroring, or log shipping. VMware and the infrastructure underneath also give you some really good options. We can simply copy over the virtual machine level backup. We can perform virtual machine level replication either on a scheduled basis or in near real time. We can also do SAN LUN level replication on the same frequency. We could also do replication inside the virtual machine. There are a lot of questions that need to be asked at this layer before you can figure out which option or options work best for you. Disaster recovery is most certainly not an easy one-size-fits-all architecture. It might even change based on the server you're looking at. It must work for all the organizational teams within it as well as the application owners. First of all, who manages your DR architecture today? What does the current disaster recovery strategy look like? I ask us very carefully because in some organizations, a single team manages every facet of the disaster recovery portion of business continuity. They would rather have a single group managing it with degraded SLAs instead of improved SLAs with fragmented operations around the process. Does the current disaster recovery architecture meet or exceed the defined SLAs that I had you force your C-level to determine and document? None of these are easy questions. It will take a concerted effort in working with every member of the organization and the application owners to determine what the appropriate management strategy looks like for your disaster recovery architecture. Here's the hardest part. How do your SQL servers fit into your organization's availability and disaster recovery strategy? Is it important if the SQL server is up when the application servers are not? Every team of people around the applications and databases need to be a part of this discussion. Do we have a one solution that can work for all servers? What HA and DR architecture best fits your organizational SLAs while meeting your budget? Please don't overcomplicate the design or the strategy. Overcomplicating it might actually introduce more instability or problems that you would have not encountered otherwise. Finally, no business continuity strategy is considered solid unless you're able to test it routinely and not only confirm that it works, but have a good understanding of how fast the process can occur. This has to be done for all of the primary scenarios for both availability and disaster recovery. If your organization can be one of the few that properly manages business continuity, you're ready for just about everything. Next, let's move on to SQL Server licensing in Module 13 to see if we have any opportunities to reduce our licensing liabilities. Stay tuned.